Ever wish you could travel backwards in time and do things differently? Good news, the laws of physics seem to say that travelling backwards in time is the same as travelling forwards. So why do we seem to be stuck in this inexorable flow towards the future? It's time to begin our journey towards really understanding time. The laws of physics describe how the universe at one instant evolves into the universe at the next, but those laws don't distinguish between the future and the past, reverse the flow of time, and their equations work exactly the same to describe a universe in rewind. That's true from the subatomic realm of quantum mechanics to the cosmic realm of Einstein's general relativity. But if time doesn't have a preferred direction in physics, why does time seem to drag us with it and only in one direction? Why is there an arrow of time? There are two distinct ways in which we perceive the unidirectionality of time. One is external. An egg might splatter when you drop it, but will never spontaneously reassemble. Our whole universe decays in the inexorable rise of entropy as time ticks forward. The other place we perceive the arrow of time is internal. We lay down our memories in an ordered sequence of prior events. We remember the past, but not the future. Today, we're going to dive into the first part of this. How does entropy break the symmetry of time and cause the future to differ from the past? We'll follow with an episode exploring why this breaking of time symmetry on the cosmic scale defines the experience of time that we experience in our own brains. So what exactly do we mean when we say the laws of physics don't care about the direction of time? Basically, if you reversed the motion of all particles in the universe, sent them back exactly in the direction they came from, and used the laws of physics to calculate what would happen, you'd predict that those particles should perfectly retrace their steps, all the way to the Big Bang if you calculated that far. Let's look at a simple example. We're going to use our good old block universe picture, where we have 2 dimensions of space and 1 dimension of time, with time flowing upwards. The block universe just sort of exists, atemporally. The experience of time is had by looking at time slices in a particular sequence, like a flipbook. Okay, so imagine 2 particles moving towards each other, let's say electrons. They move up in time towards each other in space. When they get close, they deflect due to the repulsive electrostatic force between them. Newton's laws of motion combined with Coulomb's law perfectly describes how the electron's positions change over time. But if we flip this diagram on its head, reverse the flow of time, it still looks like 2 electrons bouncing off each other. The same equations perfectly describe the bounce in both directions, and those equations don't seem to prefer one direction or the other. So, the laws of physics don't care about the direction of time. They just describe the relationship between time slices of our block universe. Time has a symmetry in the sense that the past and future aren't differentiated by the laws of physics, and those laws don't even require time to flow. It's just another dimension like space. There is a powerful exception to this. The second law of thermodynamics states that this stuff called entropy must always increase or stay constant. Entropy never decreases over time. So the second law does dictate a direction for time. It breaks the symmetry. To see why, we'll need to review entropy. We've talked about it before, and this is a great episode for a refresher. There are several ways to think about entropy. Today, we'll talk about it in terms of distribution of energy. Energy can take many forms and can be transferred between forms and between objects. For example, kinetic energy is transferred between our electrons when they collide. Over time, energy tends to get shared out as evenly as possible due to, say, collisions. So if you had many electrons in a box and half of them had a lot of kinetic energy, were moving fast, while the other half had none, then pretty quick energy would be shared out and it would stay shared out. It's very unlikely that through random collisions half the electrons would get all of the energy and the other half would end up with none. So if you start from a situation where energy is not perfectly randomly spread out, then over time it'll become more spread out. Entropy measures how randomly distributed the energy in a system is. Higher entropy means more random. The second law of thermodynamics tells us that entropy just must increase over time, which means that a system that starts out with a very specific non-random state will tend to become more random. It's a statistical effect. It's possible for small fluctuations to happen, local drops in entropy, but the larger the system, the less likely it is for entropy to reverse. So, how does this set the forward direction of time? Well, actually it doesn't. The second law just tells us how a system is likely to change from a position of low entropy in either time direction. To understand why one particular direction ends up being chosen, we need to return to the block universe. Let's start with a handful of particles with low entropy. You can do low entropy by having a weird distribution of velocities, but you can also do it by clustering the particles in one spot in the available space. Let's give those particles random velocities and see what happens in the following time steps. Even though the velocity is pointed in random directions, the cluster will inevitably disperse. Entropy increases as energy spreads out to all possible states, in this case towards all possible locations the particles could occupy. In this case, we defined the up direction in the block universe as towards the future. But what does that look like going backwards in time? Well, actually, exactly the same. Random velocity directions will tend to spread the cluster apart in both time directions. Again, if you take any low entropy system and look at steps either before or after it in time, entropy is likely to be higher. Entropy actually doesn't care about the direction of time any more than the other laws of physics. It just wants to increase in adjacent time steps in either direction. But if you live on either side of that starting low entropy point, you perceive an asymmetry in time. Particles expanding, entropy increasing on one side, or particles converging and entropy decreasing on the other. Zoom in to individual particle interactions and you see the perfect reversibility of the laws of physics. But zoom out and time's arrow emerges. The presence of an entropy minimum dictates the arrow of time. On either side of that minimum, the universe is overwhelmingly likely to evolve in a very particular way. The real-world situation represented by this diagram is called an entropy fluctuation. We experience entropy to decrease very occasionally, and typically on very small scales, due to random alignments of particle trajectories or however else the energy is moving around. Entropy can decrease, reach a minimum, and then it will be seen to increase, now on both sides of the point in time of that minimum. Okay, what does all this mean for our universe and the universal arrow of time? Well, it's no accident I chose expanding particles to illustrate evolving entropy. When we measure the velocities of particles across our universe, in the form of galaxies, we don't see random motion. We see galaxies racing away from each other, which means they were once more closely clustered. This is the expansion of the universe, and it's a manifestation of the second law on the largest of scales. We know that entropy was lower in the past because we can trace the positions of galaxies and the particles that comprise them back and calculate a much denser, more special arrangement. In fact, an incredibly low entropy arrangement. That would be the Big Bang. Given that knowledge, it's not surprising that entropy is increasing in what we now think of as the forward direction of time in our universe. So this is one argument for the direction of the arrow of time. If we think of time as just a series of instances, slices of the block universe connected by the laws of physics, then we can break the symmetry in the direction of time if one of those slices has a very unusual arrangement. The universe must get less special in either direction. So someone looking at the universe from either side of that entropy minimum would see a directionality to time. Okay, so in our universe, what caused this initial special arrangement, this extreme density of the Big Bang and its corresponding ridiculously low entropy? This is actually an open question in physics, and we're not going to address it right now, but one possible consequence is that if you trace all particles backwards in time to this original special slice, at which velocities are all random, and keep tracing out the other side, then you should see entropy increasing again, but now backwards in time. It's not crazy to imagine a symmetric universe in which those particles fan out again like a reverse Big Bang. This might be the case if the Big Bang resulted from an insanely improbable universe-sized entropy fluctuation. There's no evidence that this is true, but if it were true, we're presented with a fun scenario. If entropy increases backwards in time before the Big Bang, does that mean time ran in reverse before the Big Bang? Would that reverse Big Bang lead to a time-reversed universe? It's not entirely crazy to think so, but first you need to explain one thing. How is the thermodynamic arrow of time, the flow of time defined by increasing entropy, connected to our sense of the flow of time? Why do we experience time sequences pass in the same order as the increase in entropy? To understand why we only remember the past and not the future, we need to delve deeper. In fact, we need to delve into information theory and quantum entanglement, so we probably need another episode, or more than one, because on space-time we've always given plenty of time to space. But it's timely to spend time on that fascinating dimension that deserves more space. Time. Hey guys, so we're going to be taking a short release break for Thanksgiving here in the US.